This is going to be a little bit of a marathon. This is a compilation of compilations in a way. I'm calling this topic matrix facts, but really it's just all of the multiple choice questions, that take multiple parts of the syllabus and kind of smush them together and pretty much make you solve 5 true or false statements all in one go. So as time goes on, the explanations will definitely be getting shorter if we've already gone over that same kind of principle earlier on in the video. But for now we're going to be solving everything, which is great. Okay, let A and B be two 4x4 matrices. Which of the following statements is always true? Okay, so here's an example of kind of a strategy for solving these problems that you have to use some of the time in MA265 just because there are so many different weird things that they can come up with. Like, you don't want to go try to test whether any the sum of two matrices, if that sum is singular, then are the two matrices that you can decompose it into singular? You don't want to go test that, but reading that, it seems really iffy. It doesn't come off as true. And so what I'd recommend is go through the rest of the problem and try to find the one that you're pretty sure is true or you've seen somewhere else in order to be able to say, okay, A just must be false then. So we're going to come back to A if need be, because that doesn't really seem true at this point. What about B? If AB is symmetric, then BA is also symmetric. Yet another case where, it doesn't really seem true. In fact, no, I don't really have a good one for that. What about C? If A and B are similar matrices, then the determinant of A is the determinant of B. Well, this is one that we can prove, thank God, because we know that for similar matrices A and B, there's some invertible matrix P such that A is equal to P, D, or we're using B here, P, B, P inverse. And we've had some questions before where they've asked us, they've given us this expression, they've given us B, and they've asked us to find the determinant of A. And what you find is that the determinant of A is just exactly equal to the determinant of B. And so this is actually true, which is great for us because we were not like in A and B. But D we know for sure is false. There's no way to prove that A will always be invertible because it's an arbitrary 4x4 matrix, and thus there's not necessarily a way to get rid of A by multiplying the left by A inverse on both sides. What about E? If AX equals B is consistent for some B not equal to 0, then A is non-singular. Nope, no, not really. What if we have a 3x3 matrix with entries 1, 0, 0, 0, 1, 0, 0, 0, 0? So what this will do is take in all of R3 and output it on the xy plane. And we see really quickly that the determinant of this matrix is 0 because the values, multiplying together the values on the main diagonal gives us 0. So the matrix is singular, but it's consistent for all B that live in that output space in the xy plane. So this is definitely false. And okay, moving on. Which of the following statements are always true? Those are words I'm going to really be hating by the end of this one. If A is an m by n matrix, then the solution space, the set of all solutions x to ax equals 0 is a subspace of Rn. So all this requires you to remember is that the column space is a subspace of the number of columns, r to the number of columns of your matrix. And since we have n columns in our matrix, the null space here is a subspace. If this was r to the m, then this would be false. Okay, 2. If A is non-singular if and only if A is the product of elementary matrices. Well, this is just a product of invertible matrices. I'm pretty sure one of the points of the invertible matrix theorem that any invertible matrix is the product of an elementary matrix the product of elementary matrices. Now, the problem is If you were to ask me right now what an elementary matrix is, I would have absolutely no idea. I have no clue. I cannot remember. And right after this video ends, I'm going to need to look that up. But that's the only time this has ever come up. The word elementary. It's the only time we've ever seen it in the past 3 years of exams. So hopefully I'll be good on that. But no, this is true, but sketchily true. Okay, 3. If A is an n by n matrix and K is a scalar, then the determinant of Ka is equal to K times the determinant of A. Nope, 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 nope. In fact, the rule for this is the determinant of Ka is equal to K to the n times the determinant of A. And why is that? Well, K times A means that, let's say we have a 3 by 3 matrix, we're multiplying the first column, or row, you can think about it either way, by K, we're multiplying this by K, and we're also multiplying our third column by K. So in total, we are multiplying our determinant by K to the power of whatever matrix, whatever dimension of matrix we're dealing with. So yeah, K to the n will give us that expression. So no, this is not true. It would only be true for the n equals 1 case. What about 4? Let A be an m by n matrix, then the row space of A is orthogonal to the null space of A. Yep, that's a fact. That's a fact you should definitely have in your head, and yeah, remember that. That's a thing. The row space is always orthogonal to the null space. Don't have much to say about that. I don't even have a good mnemonic to remember it with. That's just a thing that comes up pretty often that you should have in your memory bank. Okay, 3. Let A be an m by n non-singular matrix. Which of the following statements must be true? So if we have a non-singular matrix, that means it has a determinant. So I agree the determinant cannot be 0, but yeah, no. So the determinant equals 0, that does not work, because when we take our inverse, we're multiplying by 1 over the determinant of our matrix, and 1 over 0 will give us some real issues. What about 3? Ax equals 0 has infinitely many solutions. So a non-singular matrix is that's m by n is full rank, meaning that we have a pivot for, 0 is everywhere else, but we can reduce our matrix down to the point where we have a pivot all the way down the main diagonal. And as a result, if we were to set up our equation for rank and nullity, that rank, which in this case is equal to the number of columns we have, so rank plus nullity is equal to columns, these two are equal to each other, rank and columns, thus n has to be 0. And therefore, there's only the trivial solution, x equals 0, the 0 vector for ax equals 0. So this is not true. What about 4? Ax equals b has a unique solution for every n vector b. Okay, so really what this is asking is, is our matrix 1-to-1 and onto? Is the transformation represented by our matrix 1-to-1 and onto? And so we know that any invertible matrix is reducible to the identity matrix, and we know that the condition for a transformation to be 1-to-1 is that the columns of our matrix are linearly independent. And we know that our columns are linearly independent because we have a pivot in every column. So that works. And additionally, our columns also span our output space because we have n pivots and our output space is r to the n. So spanning the output space means that our transformation is onto. Thus, the transformation is both onto and 1-to-1 for any invertible matrix. Thus, it has a unique solution for any vector b in that output space. What about 5? A must be row equivalent to the identity matrix. Well, we were using that fact just a second ago. So yeah, that's true. And you can go test that for yourself if you really want some more proof on that. I'm not going to go do it here. 1, 4, and 1, 4, and 5 is our solution there. Here is A. Which of the following statements is false? For arbitrary matrices BC, BA is equal to BC, then A is equal to C. Well, we know nothing at all about B, so the only way that this would be true is if B was invertible, so that we could go multiply the left side of both of these sides by B inverse. So B inverse BA is just equal to A, which is equal to B inverse BC, which is equal to C. So that would work only if B was invertible, but we have no data about B. B could be the 0 matrix for all we know. So no, this does not check out. A transpose is invertible. Well, remember that taking the transpose doesn't change the determinant of our matrix. The determinant of this matrix right here is non-zero. Thus, A transpose will have a identical determinant, and thus it will also be invertible. Also, we're looking for the statement that's false. I should have read that. So we already know that A is false. Let's go look at these other ones, though. C, for arbitrary matrices BC, then AB is equal to AC. Then B is equal to C. Well, this works because since A is invertible, we can multiply the left side of both sides of this equation here by A inverse. Thus, B would be equal to C because A inverse A will just turn into the identity matrix and go away. So that's true. Additionally, yes, this is a property that we know. A inverse is equal to A inverse A, which is equal to the identity. So that's true. And A inverse is an upper triangular matrix. Well, we can just go and test that. But in fact, we don't need to really write anything down even, because we know when we're taking the inverse of a 2 by 2 matrix, the A and the D positions will swap. We will change the sign on our B and C positions, and we'll multiply everything by 1 over the determinant. So we will get, for this position, negative 0 over negative 3, which is still 0, and all we need for an upper triangular matrix is for every value, every entry below our main diagonal to be 0, which it is, so that's true. So A is false. 17. A is an n by n matrix. Which of the following statements is or are always true? If A is diagonalizable, then A must have n distinct eigenvalues. Nope. This is not true. If we have an eigenvalue with a multiplicity of 2, and that eigenvalue has 2 corresponding eigenvectors, then that will still work for our diagonalization. So if we have a 3 by 3 case with lambda 1 equals 2, lambda 2 equals 1 with a multiplicity of 2, and from this we get 2 eigenvectors, and from this we get 1 eigenvector. All we're looking for is for the total number of eigenvectors, so the total dimension of all of our eigenspaces added together. We want that to be equal to the total algebraic multiplicity of all these roots here. In this case, we have multiplicity of 1, multiplicity of 2, so we're looking for 3 eigenvectors. We found 3 eigenvectors, thus these eigenvectors can span r to the n, and our matrix is diagonalizable. So we can have fewer than n distinct eigenvalues and still be diagonalizable, so that's no good. What about 2? If A is a matrix with all real entries, then all the eigenvalues of A must be real. I disagree. Let's look at this matrix, 0, 0, 1, negative 1. If we find our eigenvalues, we'll be solving negative lambda times negative lambda plus 1 is equal to 0. Lambda squared plus 1 is equal to 0. Lambda equals plus or minus I. Look at that magic. We just got imaginary roots from a real matrix. So this is false. What about 3? If A is a symmetric real matrix, then it must be diagonalizable. Well, there's a quick little video that I just finished recording all about symmetric matrices and their properties. And the first one, guaranteed by the spectral theorem of symmetric matrices, is that all symmetric matrices are orthogonally diagonalizable. And that is true because the algebraic multiplicity of every root for every eigenvalue for a symmetric matrix must be equal to the total number of eigenvectors that you get by solving A minus lambda I. And as a result, we'll always get enough eigenvectors to span R to the n, and we're good. Yeah, so if you're not too sure about your symmetric matrix stuff, go watch that. There are a couple of little nuances that don't come up in this question about those. So 3 only is our answer for 17. 2. Let A be an n by n singular real matrix. Which of the following statements are always true? So a singular matrix, by definition, has a determinant of 0, because if it did not have a determinant of 0, we could safely divide by that determinant and get our inverse. So, yep, determinant of A must be 0. A is only row equivalent to the identity matrix if it is invertible. So this is false. 2, AX equals 0 must have non-trivial solutions. That's true, because instead of row reducing to the identity matrix, let's say we had a 3 by 3 non-invertible matrix which reduced to that. You'll see that if we do our same rank nullity calculation, rank is 2 plus nullity must be equal to the number of columns, which is 3. So nullity must be equal to 1, and as a result, AX equals 0 must have infinite solutions, as there must have been an infinite line of vectors that all got smushed onto the origin when our transformation took place. So, yep, agree with that. And AX equals B has a unique solution for every B in Rn. Well, nope, not really, because you'll see we can use this matrix as an example, and in fact, this is exactly one I was using earlier. So this is kind of a redundant explanation, but this matrix, as a transformation, takes in all of Rn and spits out takes in all of R3 and spits out R3, but only the x and only the xy plane. And why is that? Because it takes our first basis vector, which started at 1, 0, and puts it at 1, 0, 0. So it doesn't move it at all. Takes the second basis vector that used to be on 0, 1, 0, and doesn't move it at all. It keeps it at 0, 1, 0. And then the third basis vector, which used to be at 0, 0, 1, it moves it down to 0, 0, 0. So you can see that the area spanned in between here is just the xy plane. And going back to option 3, that line of vectors that I was talking about that got smushed onto the origin is exactly this line on z here. Any vector up here will have its z component multiplied by 0, and so it will end up on the origin. And so if we have a b that's up here that has any non-zero value for z, it will not have a unique solution. There will be no solution for any b in Rn. And additionally, if we had a vector in the xy plane, we wouldn't have a unique solution. Still, we would have infinitely many solutions, because for every point here, there's an infinite point of z values that all got smushed down on there. So 1 and 3 should work for number 2. 21. For this matrix A, which of the following statements is true? A is both invertible and diagonalizable. Okay. Since for all of these options just have to do with whether or not A is either invertible or diagonalizable, I gotta reiterate something that comes up a whole lot. But I gotta burp first. Sorry about that. Invertibility does not imply diagonalizability, and diagonalizability does not imply invertibility. They are completely unrelated to each other. Okay, now that we got that out of the way, let's try to figure this out. This matrix is obviously invertible because its determinant is 25. Let's see if it is diagonalizable, though. Since it's an upper triangular matrix, the entries of its main diagonal are its eigenvalues, so lambda is equal to 5 with a multiplicity of 2. If we plug in lambda equals 5 to a minus lambda I, we would expect or hope to get 2 free variables. If we end up with 2 free variables, we will get 2 eigenvectors, and we need 2 eigenvectors to be able to span R2 so that we can diagonalize A. but we only get one eigenvector here. We see that x2 is equal to 0, and since x1 is our free variable, there is the only eigenvalue that we get. So it is not diagonalizable, but it is definitely invertible. What about 23? Let A be an n by n matrix. Which of the following statements is not equivalent to the fact that A is invertible? Okay, an invertible matrix can be reduced down to the identity matrix. That's going to be helpful for this. Well, the columns of A are linearly independent just simply because it can be reduced down to the identity matrix, which has a pivot in every column. So I'd agree with that right there. You could also go down the path of remembering that the transformation encoded by A, if A is invertible, is always onto and one-to-one. And the columns of A being linearly independent is that necessary condition for A as a transformation being one-to-one. A is diagonalizable. Well, what did we just talk about up here? Diagonalizability does not imply invertibility and vice versa. So nope, that's not true, or not necessarily true. What about 3? The columns of A form an orthonormal set. Nope, no. I don't agree with that. I can make you a quick matrix. 7, 3, 1, 21. Oh, sorry, that's non-invertible. What about literally anything else there would work? This matrix has a determinant that is not 0, so it's invertible, but do its columns form an orthonormal set? No. 1, the columns aren't even orthogonal, and 2, they're not orthonormal. They're not normal because the length of this guy is root 50, the length of this guy is root 10, so no, not at all. That was just kind of crazy. Okay, 4, the dimension of the null space of A is 0. We're going back to the fact that any invertible matrix can be reduced to the identity matrix. We know that the nullity of our matrix plus, in this case, 2, the rank of the matrix, must be equal to the number of columns, which is 2. Since every column always has a pivot position in it, the null space will always be 0. Oh, so this is true. And then 5, the linear system AX equals B always has a solution for any B in Rn. That's true because A, the transformation encoded by A, is onto. So it will have at least one solution for any B in Rn. And because it's also one-to-one, that solution will be unique, but that's not what we care about here. So 1, 4, and 5. 1, 4. Oh wait, interesting. What did I screw up? Not equivalent. Oh, which ones are not equivalent to the fact that A is invertible? Yeah, 2 and 3. I just inverted my my answer picking there. That's something to worry about too. If there had been an answer for 1, 4, and 5, I totally just would have picked it and moved on. That's kind of scary. Okay, yeesh. 13, which of the following statements are true? If lambda is an eigenvalue for A, then negative lambda is an eigenvalue for negative A. So here's a nice little fact. If you multiply, let's say that lambda 1 is an lambda 1 is an eigenvalue of A, then C times lambda 1 is an eigenvalue of CA, where C is any non-zero, maybe it could also be 0, but for our purposes, non-zero constant. So if C is equal to negative 1, then this condition holds exactly. So there we go. What about 2? If 0 is an eigenvalue of A, then A is not invertible. Well, yeah, this is true. You can think about this geometrically, or you can think about this on a matrix level. We know that every invertible matrix is reducible down to the identity matrix. And I'll just use an upper triangular example for this, but it will work for a more general case. Let's say we have 1, 2, 0 on our main diagonal and 4, 7, 3 there. So the determinant of this matrix is the product of all of its main diagonal elements, which is 0, so our matrix is non-invertible, but also we know that the eigenvalues of this matrix are its main diagonal because it's upper triangular. As a result, we see that 0 is an eigenvalue and A is not invertible. Yes, so A is singular. So graphically, you can think about this as we know that A is only invertible. We know that A is only invertible if its null space is zero-dimensional, but having an eigenvalue of 0 means that there is some vector in Rn, that when we apply the transformation gets scaled by that eigenvalue, which in this case is 0. So taking that entire vector, scaling it by 0, will just smush it right onto our origin, which means that we will have infinite non-trivial solutions for ax equals the 0 vector. So yeah, that is true. What about 3? If an n by n matrix A is diagonalizable, then A has n distinct eigenvalues. Remember, we talked about this a bit ago. Having n distinct eigenvalues will make your matrix diagonalizable. So this is not inherently an incorrect statement in that this statement right here implies that A is diagonalizable, but remember that A can have fewer than n distinct eigenvalues. It can have an eigenvalue with, say, a multiplicity of 2, as long as that eigenvalue has 2 associated eigenvectors, so that A minus lambda, or that the matrix A is not defective. That's the term that we use for it in MA 266, and it's a fun one. Okay. So this is false. We could have fewer than n distinct eigenvalues and still be diagonalizable. Okay, 4. There's A. A is both invertible and diagonalizable. Well, this is exactly the same kind of case as the 0, 5, 5, 1 thing that we had here. So we can already know that this thing isn't diagonalizable because our eigenvalues are 2 with a multiplicity of 2 when we plug in 2. The only case in which this would be diagonalizable is if we got 2 free variables, but since we only have 1 free variable, it is not diagonalizable at all. Okay, so that leaves us with 1 and 2. 3. Which of the following statements is false? Ooh, this problem is a weird one. This is from 2019 fall. Yeah, it's you'll see. If V1, V2, V3 is linearly independent, then V3 is a linear combination of V1 and V2. So the nice counterexample with a tiny little graph up here is, okay, so if we're dealing, actually we kind of want, it's linearly dependent. Yeah, okay. Let's go in 3 dimensions for this one. So we're looking for a case where we have a linearly dependent set where V3 is not a linear combination of V1 and V2. Okay, here's the simplest one. V1 is the 0 vector. V2 is the 0 vector. V3 is a non-zero vector. There is no linear combination of V1 and V2 that you can use to form V3, yet our set is still linearly dependent because V1 and V2 lie on each other's span. So this is false, which is great because the rest of these get a little sketchy. Okay, B, suppose that the columns of A are V1, V2, V3, then the matrix equation given there is equivalent to this vector equation. Well, if you just replace A with what we know about A in terms of its columns, V1, V2, V3, if we just do this multiplication, if we just multiply this out, we get exactly this. So that is true, so it's not our answer. What about C? This is the weird one. Suppose that x0 is the solution to the linear system ax equals b, then the set of all x such that ax equals b is equal to x0 plus the set of all x such that ax equals 0. Okay, so I think that my previous way of explaining why this one is false, is true, is sufficient here. So let's see if I can remember what I said. Okay, so we have x0, which is a solution to ax equals b. Let's just do a 2-dimensional example. Let's say that ax equals b forms a line here. So this is the line. Can I just make this in matrix form? I don't think I'm good enough. for that. No, it should be. Yeah, yeah. So this really encodes moving the first basis vector from 1, 0. Let's move it up to 1, 1, and move our second basis vector from 0, 1 also over to 1, 1. So that kind of gives us this single span there. Okay, so it's telling us that the solution set for ax equals b. Let's say ax equals b is the position vector. That b is the position vector pointing here. Then ax equals b is x0 plus the null space there. Okay, so the important thing to think about here is that the null space is the set of all vectors that when we apply the transformation will end up on our origin. And so I'm pretty sure that geometrically this is the correct line. All of these vectors will get squished down onto the origin, and then we're finding the set of all solutions such that ax equals b. All we're really doing when we're doing this is taking the vector that under our transformation leads to b, and then adding this whole set. So this entire set of vectors here. So what that will just serve to do is, as far as I can tell, shift that solution set over in a way to b there. And so this does check out because the set of all vectors that end up on this point should be this infinite line as well, because we'll have infinitely many solutions for all these points. Yet again, just like we were talking about with the first question in this packet, sometimes you kind of just have to be like, okay, this question is this answer choice is correct, or this answer choice is definitely wrong in this case, so we can choose it. And I'm pretty sure that C is correct, but we're more sure that we're correct because we know that something's true rather than we're sure that something's false. You know what I mean? So this is that should be true. Okay, D, the columns of A are linearly independent if and only if A has a pivot position in every column. Yep, that's true. That kind of implies graphically that every column has control over some dimension or way of movement that none of the other columns in the matrix do in the same way. So they are linearly independent from each other. I agree. What about E? A homogeneous linear system has a non-trivial solution if and only if it has at least one free variable. Yep. If we set ax equal to 0, then solving for our null space, so the linear system will only have a non-trivial solution. We know that that corresponds to the null space having a dimension greater than 0, and that will only occur if we have at least one free variable, so that our rank, let's say we have one free variable, our rank will be the number of columns minus 1. So let's say we have 4 columns, we'd have a rank of 3 plus the nullity is equal to 4, and so thus nullity must be non-zero. 20. Which of the following statements are true? If 2 by 2 matrices A and B have the same eigenvalues with the same multiplicities, then A is similar to B. This one I got wrong when I took this exam for the first time, and I'll tell you why. Because A seems super true. Like when you first look at it, that's like that. See, that makes sense because if we're able to take A and set it equal to PD P inverse, although they're using B here, we know that B's eigenvalues and multiplicities are the same as A because A's eigenvalues and multiplicities are exactly what are encoded down the main diagonal of B. So that seems to work, right? But the thing that I forgot to take into account is, what if A what if A has, say, two eigenvalues but only one eigenvector? Or it has, sorry, that I don't know if that's going to happen. No, that won't happen. But through one eigenvalue with a multiplicity of 1 and an eigenvalue with a multiplicity of 2, but we only get one eigenvector from each. So then we could have an A and B with these properties, but we know that A is not diagonalizable. So there's no way to write, there's no invertible matrix P such that PBP inverse is equal to A. So this will only hold true if A is diagonalizable, which it doesn't have to be. Yeah, that's a little, I'm still a little salty about that question. Okay, B, row operations on a square matrix do not change its eigenvalues. Yeah, they do. You can go test that out for yourself. I'm not going to go mess around with that, but yep, they definitely do. What about C? Here's the weird one, but it makes a lot of sense graphically. Just you wait. There exists an n by n non-zero matrix A such that every non-zero vector in Rn is an eigenvector of A. Whoa. What does that mean? Infinite eigenvectors? That's crazy. So what this is really implying is a lot easier to see or to think about if you know off the top of your head what an eigenvector means graphically. So an eigenvector is a vector that when you apply a transformation, let's say we have this initial vector here. So if we apply a transformation and that vector gets kicked off of its own span, so we can kind of note the span of this first vector here. If it gets kicked off its own span, it is not an eigenvector, or it is not along an eigenvector. But let's say that we have this special vector here where any vectors along this span will not get kicked off that span when we apply our transformation. They will be scaled by a certain value instead. So let's say that all of our vectors get scaled by a factor of 2. That means that the eigenvalue associated with that eigenvector is 2. So let's see if we can use that to reinterpret what they're telling us here. So there is some non-zero matrix A such that every non-zero vector in Rn is an eigenvector of A. So here it is. So let's say we have a transformation that takes our two basis vectors and multiplies them by 2. So we get a matrix for this transformation of 2, 0, 0, 2, where this is saying take our first basis vector that used to be at 1, 0, put it at 2, 0, take our second basis vector which used to be at 0, 1, and put it at 0, 2. So what happens to all of space? Well, all of space kind of expands by a factor of 2. So if we take any starting vector, what's going to happen? Well, its x component will be multiplied by 2, and its y component will be multiplied by 2. And no matter which vector you choose in this space, it is always on an eigenvector. Isn't that cool? So the general form for this kind of matrix is just lambda I, and you can kind of see that here. In this case, lambda was equal to 2. That's the eigenvalue that corresponds to all of these eigenvectors, where all of R2 is in fact on an eigenvector. So that's kind of cool. What about D? The numbers 1, -1, and 0 can be the eigenvalues of a 3 by 3 invertible matrix. Here's a counterexample for you to show that this is not true. If we have 1, 1, 0, and then zeros everywhere else, since this is an upper triangular matrix, we know that the eigenvalues are encoded by that main diagonal. So that gives us, our 1, -1, and 0. But we also know that since it's upper triangular, its determinant is just the product of that main diagonal. Its determinant is 0, thus it is not invertible. And we have a matrix here. Okay, is it diagonalizable? I don't really feel like doing this, but we're going to do that. We're solving a minus lambda I. I do that every time. The determinant of a minus lambda I equals 0 is 4 minus lambda times -6 minus lambda plus 25 is equal to 0. Lambda squared plus 2 lambda minus 24 plus 25 is plus 1 is equal to 0. And Yeah, this is not gonna, this is lambda plus 1 squared is equal to 0, so lambda is equal to -1 with a multiplicity of 2. If we plug that into a minus lambda I, we need to get 2 eigenvectors, so we need to get 2 free variables out of this. And the only way to get 2 free variables is if we end up with the 0 matrix here. And, we'll get 5, -5, 5, -5. That's not the 0 matrix. We'll only have 1 free variable, and as a result, this thing ain't diagonalizable because we only have one eigenvector when we need 2. Finally, last question. This was a lot less painful than I thought it was going to be. Suppose that A and B are n by n matrices. Which of the following must be true? What about A? Let's see. AB is equal to BA. Well, that's only true for what? Matrices that are inverses of themselves. So if B is equal to A inverse, then this would be true because we know that A inverse A is equal to is equal to A inverse, which is also equal to the identity matrix, or just if A and B are the identity matrix, but the inverse of the identity matrix is the identity matrix. So there's really no difference here. But the thing is, we don't know the determinant of A and B. So we don't know whether or not A and B are invertible, so we can't say this. What about B? If AB is equal to I, then B is the inverse of A. Yep. Yeah, we were just using that fact right there. Yeah, and we know that these have to be invertible because this is only true if one of these guys is the inverse of the other. Okay, what about B? If A and B are invertible, then AB inverse is equal to A inverse B inverse. Nope, this is not true. If we're taking the inverse of two matrices multiplied together, that inverse will be B inverse A inverse. We have to flip the two within the parentheses. What about D? Is this thing invertible? Let's test it out. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to try using row reduction here. The only legal things we can do with row reduction at this point is what? I gotta remember. Just adding factors of rows to other rows. That's the only thing that we can do that's not going to change our determinant. But actually, we don't care what the determinant is. We just need to make sure that the matrix reduces down to either the identity matrix or not the identity matrix. So let's figure that out. Let's subtract 4 row 1s from row 2. That gives us a 0 here. Minus 8 is -3, and minus 12 is -6. So this can become 1 and 2. We can subtract here, get 0, -1. Subtract 7 row 1s. We get 16, that's 1, 2, which we can use row 2 to set to 0, 0. Since we only have 2 pivots, this is not invertible. What about E? Finally, if AX equals B is consistent for some B in Rn, then A is invertible. Nope, nope, nope. And we will come back to the example that I've used a couple times now. This guy that takes in all of R3 and outputs the XY plane in R3. So it's consistent. It's consistent for any vectors B that happen to lie in the xy plane, so any vectors with a z value of 0, but it is not invertible because it's upper triangular, so its determinant is just the product of its main diagonal, which is 0. So nope. Yeah. Okay, we're done. This is quite the slog, but we made it.